Hey everyone, welcome to session 11 of our ANSYS Fluent course for beginners. Today we're going to tackle something really interesting, a small-scale solar chimney simulation using the discrete ordnance radiation module. Now I know that might sound like a mouthful, but don't worry, we're going to break this down step by step. Before we dive into the actual simulation, we need to understand some fundamental concepts about radiation heat transfer. This is super important because radiation is the key driving force behind how solar chimneys work. In this session, we'll start with the basics of radiation, understand how it works in ANSYS Fluent, and then apply this knowledge to simulate our solar chimney. The discrete ordnance model we'll be using is particularly good for this kind of application, and you'll soon see why. I've structured this tutorial to make sure you get both the theoretical background and the practical skills you need. We'll begin with radiation basics and gradually work our way up to the actual simulation setup. Alright, let's start with the basics of radiation heat transfer. At its core, radiation is simply the emissions of energy as electromagnetic waves. Pretty straightforward, right? Now, there are two really important things about radiation that make it special. First, and this is fascinating, radiation can occur in a vacuum. Unlike conduction or convection, it doesn't need any medium to transfer heat. Think about it, how the sun's heat reaches Earth through the emptiness of the space. That's radiation at work. The second key point is that any object, and I mean any object, that's above absolute zero temperature emits energy through radiation. Yes, even this desk I'm sitting at is radiating energy right now. It's just that we can't feel it because the energy level is very low. Looking at the examples on your screen, you can see three practical applications where radiation is super important. We've got a solar load simulation for HVAC systems, a headlight analysis, and a glass furnace. These are perfect examples of where understanding radiation becomes crucial in engineering. Take the glass furnace, for instance. It operates at such high temperature that radiation becomes the dominant mode of heat transfer. Or the solar load case. This is particularly relevant to our solar chimney project, as we'll be dealing with similar physics. In the next few slides, we'll explore those concepts more thoroughly and see how ANSYS Fluent helps us model these radiation effects. Now on this plane, I can create my own sketch that I want to use in order to actually split the face on the front side. So this time maybe line tool could be enough. I just draw a line like this. And within the dimensions tab, we could actually specify its exact length, which is 1 meter. Then I get back to my modeling tab, and from the tools tab, I want to find the face split tool. And now you can see that we have denser grid near the inlet, and we have a growth rate up until we reach the final outlet. And also from the other direction, you can see we have denser grid near the glass. And this was actually what we wanted. And let's check the number of elements. It's more than 160,000. So our model is actually placed in Sheffield of England, and through the web you would find the geography coordination. So the software asks for the longitude, the latitude, and the time zone. It's time for the boundary conditions. This is one of the controversial parts when it comes to radiation module. So concentrate and follow me step by step. This is very important. And I want to start by the pressure inlet. So as you can see in here, and we mentioned in the introduction, when it comes to a wall, you can see a part of the irradiation will be emitted, a part of it will be reflected, a part of it will be absorbed by this wall, another part will be transmitted. So we can say that the sum of the radiation, I mean the reflection, the absorption and transmission would be 1. And we can see that right here. But for example, the part of the reflection could be categorized into two distinct patterns. It could be diffused or it could be actually reflected through this specular reflection mechanism. And these are the parameters that we needed. So as you can see in this software, we need to specify the direct visible, absorptivity, the direct IR or infrared, and also the diffuse hemispherical. So once again, if I get back to this table, you can see that we've got it for different incident angles. And there is another point that lies in Fluent. Whenever you want to specify these parameters, you have to consider a normal incidence angle. Very well. So let's check the results together. As you can see, just after 600 iterations, I myself manually stopped the solution to check the results. You can see the residuals. Of course, they've got a perfect convergence, and this is the results of professional meshing and setting up all the solver settings that you can rarely find, especially when it comes to radiation module. So let's check the reports. You can see the glazing temp, it reaches a constant value and is stabilized. They also, same thing happened for the velocity at the outlet and exit of our solar chimney. And finally, the volume report, which could be the most challenging one to reach convergence, just converged after 200 iterations. And this is simply perfect. So let's check the results together. First of all, I want to start by checking the temperature inside the solar chimney. So regarding all the parts and components that we have, including the absorption wall and also the glass or glazing wall, you can see the temperature inside reaches 305.5 Kelvin. Consider that the outdoor temperature was 300 Kelvin, and we could have actually increased the temperature inside the solar chimney by 5.5 Kelvin regarding the atmospheric temperature. And this is one of the greatest parts when it comes to accurate solution, and you really enjoy these results. Then for the alpha temperature, or better said, the alpha velocity, you can see this could actually result in 0.72 meters per second velocity. This is not low because we didn't have any force inlet, and it just happened based on natural convection inside the solar chimney. And another one, which we call plane XY, change the method simply, and right now it is not in the middle. Regarding the scale that we have along the z-axis, you can see it is 0.2 meters. So we have to change it to 0.1, and I guess then it would be exactly in the middle, right? So let's see what just happened inside the solar chimney. So for now, this can show us we could successfully design the solar chimney, and we could make the best out of this ambient temperature. And if you want to check the distribution better, you can uncheck the outer range and also the clip to range. And now you're able to specify this range for yourself. So I want to keep it, for example, from 300 to 320 to see what just happened. Very well, you can see the cold weather that is coming from the ambient, and as it reaches and rises through the solar chimney, it actually gradually increases. And this is the main point of using the solar chimneys. We can see that on the other plane as well.